My name is Mehar Jaiswal, and I'm the lead partner of AuroraNautics. I'll be discussing the making of our uncrewed ground vehicles using PX4. Many of the drone industry uses Dronecode for drones, ROS for rovers. At AuroraNautics, we thought, why not use the same common code base for ground vehicles and air vehicles? We believe that the combination of both open source projects is what will give us the best initial being able to architect both products. Due to the interest of time, I will not be able to cover the entire process, but I would like to mention that the majority of the setup was based on the PX4 NXP Hovergames and the NavQ Git books. The setup is very well documented on these websites, and it's very useful for those of you that are starting out. We also use the Traxxas Stampede kit to build up this rover. We used the base of that Traxxas Stampede and then removed the case on top to be able to put all of our. The radar, lidar, and camera perception head is the heart of our. What you see is an early prototype where we use stationary perception, and the lidar is not shown because we added that later on. We engineered our perception head to physically look in the direction of intended motion, so it rotates to be able to see. The reason is to do this is to have one compact assembly so you can lower the cost and still achieve a lot without having to have multiple. We have taken all of this and put it on top of the rover. The perception head sits on top and aids us in finding active targets in the field. The radar, lidar, and camera work together to create a robust sensor system. This also brings us to, again, the purpose of building this rover. We started out making a static capability of the head to work. We then worked on scaling it to be able to work on. Our end goal is to be able to put this perception on the drone so that we can perceive objects on the ground. The Traxxas Stampede is an RC car that we used, and it's very inexpensive, and a lot of the controller setup was already configured, so we were able to use it straight out of the box. For our rover, we were able to remove the case and then add all of our components on top and then retrofit this little RC car into the rover you will see in just a second. So the Ardu rover and Stampede projects were very well documented online, and that's what we used in the early stages. It was very useful. This is our rover, and this is the aftermath of all of that retro. On top, we have added a robotic arm, LiDAR, RTK GPS, camera, radar, a battery pack, and of course this sits right on top of that Traxxas frame. The beauty of these features is how far we are able to enhance our perception capabilities. Even though we used a Traxxas base, we added a lot of things on top. You might say that this frame is way too small for all those components, or perhaps you should be able to scale it for a larger rover. This can be scaled since the perception head is all one assembly, so it can be put on things large as a golf cart. The robotic arm was added for a particular application, but the main feature is the perception, the radar, lidar, and camera. This is because it can be used for multiple applications and why it is so important to us. We also have a navigation computer, which is the NXP NavQ, and we have the Nvidia Nano, and it's located on that black box on top. And we also have an ARM microcontroller that controls, and we have an Ethernet and USB built into the hub. There's also an RC radio and Wi-Fi. So this particular drone was made for the drone recovery application. It was made in partnership with a few students from Texas. In August, a few weeks ago, our Airogistic partner, Jeff Michalski, and our AuroraNautics partner, Sumaid Mahmood, were able to be a part of the booth at AUVCI. This was sponsored by Dronecode, and they had the pleasure of meeting Raymond. We announced this product at, we also announced the launch of our rover at the show. So we were able to study all types of perception and combination of the perception features. We started out with just visual sensors and cameras and LiDAR, but the more we looked at it, the more we realized that the real world environment were greatly skewing. That is why more robustness. In our testing, we were working with both visual sensors and RF, and we perceived that the RF will work in all types. We're also developing our own RF called Aurora. So there's two important things when it comes to perception sensors. Number one is speed. How fast can we gather and send data? And number two is distance. How far can we see the rover? So when we think of the combination of all of these sensors, we want to be able to pick a combination that is optimizing both speed and distance. In QGoundControl, we picked the rover Airframe. Airframe is kind of a misnomer in that the selections include ground vehicles, air vehicles, and water vehicles at times, so you don't really have to constrain yourself in picking only the vehicles that fly. Under the rover Airframe, we picked the generic vehicle. So this is an overview of the vehicle setup summary where we picked settings for our airframe, our sensors, radios, flight modes, power supply, safety, and camera. Setting up the rover was a lot easier than setting up an aircraft or drone. There's not a lot of sensor checks and calibration, like, for example, gyros and accelerometers. So, you're still welcome to do that, but the rover profile did not enforce this. So due to the interest of time, I won't be able to go through the details of the vehicle setup, but the back of this slide deck has all that information. So you're free to download the slide afterwards. For our RC controller setup, we use the FlySky FSI6S RC transmitter. And of course, before any steps were made, we made sure to turn on both our batteries. First step was to turn the controller on and you would get the warning. This warning would tell you to push that throttle all the way up to full throttle position. That left joystick was spring loaded, but we took out that spring so that we could better control the speed. The Traxxas frame actually goes pretty fast, so this was our way of sort of controlling this and mitigating. The second step is to push that throttle all the way up. And then the third step is to push that throttle all the way down. You can do this before arming for the RC control. Before arming, of course, turn on that GPS and make sure that's synced up. And the last step is to use the controller with the left joystick to add gas and accelerate, and then the right joystick to be able to steer left. So this is the picture of the field where we did most of the testing. Those orange points and black lines are waypoints that match in QGoundControl and stakes in the ground respectively. In further testing, the closest waypoint will become an active target. And we are testing this rover in real life. And so in the picture, you see that it's a very sunny day, but there are days when it's cloudy. And we put a lot of emphasis on testing. Part of the challenge with navigation was that it didn't take good paths. Rover rolled through the waypoints because the speed was fast. So to fix this issue, we tried to introduce intermediate waypoints between the main points, but there was still some rolling involved. So a better way to navigate through those waypoints will be part of our future. So this is the drone dome. It is a netted enclosure that we use for testing. It is also a product that is sold by our partner company, Airogistic. We were able to test our rovers and drones within this space. Once we replicate the perception head on the rover to be put on the drone, all of our initial and repetitive testing will be done inside. Also, our landing pads could also be placed inside for perception to the landing and test as well. Okay, so when it comes to range, angle, and speed measurements, so in theory, perception is an easy problem because you're trying to measure a range and speed and an angle. And if you have a radar or a sensor that's capable of that, then you want to be able to measure the speed the object is in relation to yourself. But in practice, this can be a lot harder to solve because objects can be complex. So when you talk about the range, angle, and speed, depending on what object you're using and what sensing technology you're using to capture those measurements, you'll usually get an array of those measurements on the point of the object. And if the object is complex, you will get different ranges and different angles and different speeds, depending on where you hit it. Different sensing technologies will give you different. What you will end up doing is making a lot of those measurements, and then you'll be able to bound the object, kind of like a 3D object in space. And if you're able to do it right, you might be able to extract dimensional information about the object so that you can make a decision about where you are pointing. This is why we want to use a variety of sensors so that we can get different types of info and be able to estimate the best possible measurements and then be able to triangulate position, which would then tell us whether or not we need to move towards the object or relative to the object or away from it. In the end, you'll get lots of angles and lots of ranges and measurements, and in some cases, you'll be interested in getting points of which is what we're developing in our perception head and our rover. So we created a point of interest object called an active target, and we are now beginning to look at those highlighted points to better understand the angles and the ranges that we can get, so that we can apply them to navigation or object avoidance, among other applications. So we started out with this rover as just a test vehicle, but the more we worked on it, the more we recognized that rovers were being used for, and we could definitely. There are many purposes for this rover, such as field testing, warehouse bots, garbage picking, drone recovery. Another thing is that drones and rovers will be widely used, so they will work cooperatively to achieve such. Since many applications will overlap between the two, it will make sense to have a common platform. Going through the previous slides, I mentioned some challenges and issues we faced. The rover had some hiccups with rolling around the waypoints and could not be stationary in place, where we have added stops due to the fact that it doesn't have brakes or reverse acceleration features. It also doesn't receive precise locations of waypoints using RTK GPS as a primary position estimation. Our Traxxas base also cannot yaw, so there needs to be some accountability for the vehicle turning radius. There also needs to be new rover profiles for better configuration that will allow for yaw. For our future rover work, currently our rover works well, but there are some things we could definitely improve on. We would like to investigate reverse mode that could be controlled by the switch, controlling the speed, also making changes within mission planning to be able to incorporate rover orientation and waypoint motion accuracy. Also the ability to accelerate and decelerate to rolling. For our future perception and test work, we would like to create test environments to be able to validate our LiDAR camera and advanced camera sensors for our active targets. We also want to pursue two test cases. Number one is placing our perception head on a stationary object and then testing the range, angle, and velocity of a moving rover. And then number two is placing the perception head on the rover and then testing those same measurements for a stationary object. We will be also testing our drone rover and pads landing stations under real life environments so that we can better understand. We would like to thank NXP for the hardware and Dronecode for the opportunity to speak today. This project has really taken off this past summer, and we have accomplished a lot of what we had set out to do. With the future work and addressing some of the known issues, we're looking for groups and individuals, even in academia or in industry, to collaborate as we are looking to grow this team. We plan to be making some Dronecode contributions to ground mission planning for putting together, improvement accuracy of navigation. So we'll be putting together a Git repository, which will release.
Okay, Mehar, we're at our time, and they're kind of warning us. So you might want to skip the video. You could play it, and people could stick around and watch if they want to see Raymond driving the rover. But if there's questions, then I would invite you to get in touch with Mehar or myself. Just why don't you show the last screen real quick so they have your email?
Yes. So for any questions or inquiries, feel free to email me. Let's get in touch.
Okay. Yeah, and just play the video. People want to stay. Yeah, they can see the video from there. Okay, thanks.
Let me see. Okay, so this.
Oh, you want to ask Lauren how to let out?
I don't know if you guys can hear the audio, but this is at the AUVCI show.
Yeah, this is Raymond driving, guys. We can all blame Raymond's driving skills. Here's the handsome fellow over here driving.
Okay.
Thanks. Thank you, everyone, for showing up. Appreciate it. Bye.